oxide. You also have boron dichloride, that's a cation. So chlorine has how many valence electrons? 7, so this is 14, and the boron has how many? 3, is that right? Yeah, let's have a look. 3, and 3, and it has 1 positive, so 1 is away, it has to be ionized, so it's a 16 electron system, and with this has 1, 2, steric number 2, that's as a linear molecule. Now, a trigonal planar, steric number 3, central, and 3 bonding partners here. Is it here, here, and here? So what could that be? Boron trifluoride. It doesn't get to the octet, because it's sort of in the middle here. Boron has a hard time getting to the octet, because it has 3 valence electrons. Fluorine gets the octet, you see that? The boron trifluoride, the fluoride gets the octet, the boron not. But with this, you have 1, 2, 3 bonds, and the steric number is 3, and you can have this arrangement. It's flat, 120 degrees angle. This one you've seen before. NO3 minus. The nitrate ion, flat, 120 degrees. The nitrate sits in the middle here. NO3, see, we have 1 double bond in there, remember? There's a double bond, which is an oscillating double bond or resonance structure. So you don't count this, you count this as a bond. Yeah? So 1, 2, 3 bonding partners. With this, the angle is 120 degrees, and it's trigonal planar. So as I said, multiple bonds count as 1 effective electron pair. Now, this is acetylene. No, ethylene, isn't it, right? Ethylene. And so what is the carbon? If you look at the carbon, what's the structure here? What's the VSEPR structure for the carbon? 1, 2, 3. We are talking about trigonal, okay? It's trigonal. What's this one here? 3, okay? So this is also flat. This carbon here has this one, and this one, and each angle is 120 degrees between them. Good, let's do tetrahedral. Tetrahedral, steric number 4. This is CH4, and we know that angle is 109.5 degrees in a perfect tetrahedron. Okay, so 1, 2, 3, 4 bond partners, 109.5 degrees. Now let's come to something else, which is also tetrahedral, which you need to have 70% of it in your body. And this is water, H2O. What's the steric number on this? 1, 2, 3, 4. Each pair counts for 1. So this is actually tetrahedral coordinated. It's not just bent, it's tetrahedral coordinated. And so, but the angle is not 109.5 degrees, it's 104.5 degrees. Why is that? That's called the lone pair repulsion. So there's these lone pairs on the side, and they're pressing, this is the angle, and they are negative, they press on each other because they're not bound, they press on each other, so the negative charge goes lower down, and now it presses on that angle here, okay? That's the 104.5 degrees, okay? It presses on that angle, and so that's called the lone pair compression. Lone electron pairs compress the angle between the bonding pair. That's why it's 104.5 degrees. Now let's do another one. Ammonia, NH3, ammonia, not ammonium, ammonia is NH3, the nitrogen has 5, so 2, 4, 6, 8, that's fine, hydrogen has 2, 2, 2, so you have 1, 2, 3, steric number is 4, tetrahedral, so the nitrogen sits in the middle. One of the free electron pairs is here, and the other electron pairs are here, and they are bound to the hydrogen. So since you have only 1 free electron pair, it does not influence the other bonds, it does not deflect the other bonds so far down. It's in terms of the angle. It's 107.5 degrees, that angle here. And with this, you have the lone pair compression of 1 electron, so that is not as strong as this, so you get closer to that angle here, 107 degrees. So you need to be able to explain this if you have 2 electrons and 1 electron and no electrons in a tetrahedron. The next part, there it is, for those who have not understood this yet. So there is CH4, it's no lone pair, then you have 1 lone pair here, it compresses that angle here to 107 degrees because of the Coulomb interaction, the Coulomb repulsion. And here you have 2 lone pairs, and they compress that angle, they push on this bond, and they push on this bond, and with this you have an angle of 104.5 degrees. So the electron group repulsion is if you have 2 lone pairs, 1 lone pair and a bonding pair, and 2 bonding pairs, so that goes from here to here, okay? So the last one, no, the second to last one is trigonal bipyramidal. So the steric number is 5. That means we have a trigonal plane here, and we have this one perpendicular, and this is the bipyramid. Okay, one is this pyramid, and that's the other pyramid here. Okay, that's the bipyramid. And so you have phosphor pentachloride. Phosphor pentachloride is phosphorus in the 5th group, has 5 electrons, and so 5 valence electrons, and it coordinates with chlorine. Chlorine gets with this an octet, but 2, 4, 6, 8, 10. That's an expanded octet. So you're having trouble expanded octet. Phosphorus pentachloride has each of them 1, 2, 3, 4, 5 a chloride in there. Okay, chlorine actually. Now a tricky one is iodine fluoride. These are halogens. Fluorine and iodine are halogens, and these are interhalogen compounds. They react with each other. Of course they can, because the electronegative of this one is much higher than the iodine. Okay, so it's nevertheless a very peculiar compound. So the iodine would have, so it has 3 fluorides, so the fluorides have 8. Okay, that's an octet. But now the iodine has 7, doesn't it? So 7, the iodine has 7 valence electrons, 7, 2, 4, 6, 7, 8. What? 2, 4, 5, 6, 7. Yeah, that's correct. Okay, good. So how many bonds do we have here? What's the steric number? 1, 2, 3, 4, 5. So you set this always, most of the time you set those in the equatorial plane. You don't set them up there and up there. You set them in this plane. That's the rule. So there's a fluoride, there's a fluoride, and there's a fluoride. And here would be a lone pair, and here would be a lone pair. Are you with me? Okay, so there would be a little bit of it would be not totally linear, because they compress this angle a little bit, this angle and this angle, so it's a little bit bent, okay? And so just to show you, xenon tetrafluoride is from crystals. In the 60s, we called this, xenon was a inert gas, called an inert gas, now we call them noble gases, I don't know. The only thing they do, really, they have a filled orbital period, okay? They're at the end of their quantum number. And so, but they are very stable configurations because of that. And so you heat xenon and fluorine at 300 degrees and 6 atmospheres, you get colorless crystals, they sublime at 115 degrees. So just for you to get a little bit of education, it looks very cool. At least 20 years ago it looked cool. I didn't teach 20 years ago that, by the way. Okay. So the octahedral, let's talk about xenon again. Xenon is a noble gas. Xenon tetrafluoride. So you need something pretty aggressive, obviously, to react with this. It has 1, 2, 3, 4, 5, 6, steric number 6. Okay. Now you put them, in this case, you put them here. Okay. And with this, would this have a dipole moment, xenon tetrafluoride? Would that have a dipole moment? Hello? No. Because this one is compensated by this one, and this one is compensated by that one. Actually, I did look in the book. There's a whole page on vector addition in the book, just for those who never have seen that before. A whole page, beautiful page with blue background on vector addition. So maybe you put it under your pillow and then get it by osmosis. And sulfur hexafluoride is, so 1, 2, 3, 4, 5, 6. Sulfur hexafluoride would be also steric number 6, and this would be an octahedron. This is a typical octahedron. All right, so now let's see if you understood. We have silicon H3, silicon hydride plus, okay, SiH3 plus. So you can draw the Lewis structure for that. And then we have carbon trichloride. This is an anion, this is a cation, so you can calculate how many, or count how many electrons you have. You draw the Lewis structure, dot structure, then you define the steric number, or determine the steric number for each of them, and then you see, which angle is that, and which angle has this one, and then I ask you, theta means angle, usually in scientific notation, that's a theta, that's a Greek, large T actually in Greek, theta, and that signifies always angles, all right? So the angle of this one here, and the angle of that one, you have determined this, and then you tell me, are they the same, the angles? Is this angle smaller than this one here, or is this angle larger than this one, okay? So this is how this probably looks. I don't know how it looks, okay? So you tell me. Actually, I do know how it looks. Gotta give me everything that I taught you today. Or I didn't teach you. What is it? Okay, let's have a look. I get a heart attack immediately later. There's a trend. That's pretty good. There's a trend, okay? I don't know, maybe the trend is this way, but there's a trend. So what can I do for you? I'm not quite sure. I told you everything that I know, actually, and it's not enough, obviously. Let's think about this. Can you draw the Lewis structure? Okay, draw the Lewis structure, okay? Then you determine what the steric number is. You must have, somewhere you must have a lone pair there, okay? You determine what the steric number is, and then you look at this here, and it says, okay, the angle is something like this here, and then you compare which one is larger, and then you can answer that question. Why don't you discuss this with each other? Come on, that's important. Let's get home with success. This one should be very easy, SiH3, okay? It should be very easy. Yeah. So this, don't forget that plus here, okay? And that minus here. Don't forget to put that electron, subtract or put that electron in. Yeah, we're getting there. That's pretty good. Okay, let me explain it to you. So silicon has how many electrons, valence electrons? 4. And hydrogen 1, is that right? So you have 4 and 3 is 7, and you take 1 plus, so you have 6. You with me? Okay. So how do you put 6 electrons around that silicon? Okay. Very simple. You put them around it. 2 and 2 and 2. So you have each of them bound with the hydrogen. Okay, 6. So what's the steric number on that? So you have 1 bond, 2 bonds, 3 bonds. 3. You agree with me? What's the angle of that? 120, because it's a plane, not trigonal planar configuration. Now we come to the other one. Carbon has 4, and chlorine has 7. 3 times 7 is 21, plus 4 is 25, and 1 negative is right 26. We've got to distribute 26 around this. Try not to violate the octet rule. So each of the chlorine has a full bond with the carbon, and then don't you have one extra pair? So what would be you have 3 bound and 1 extra pair. What would be the steric number? 4. Okay, steric number 4 is 109 is tetrahedral, 109.5. Which one is the larger angle, 120 or 109.5? So that must be the answer here. Let's see if that is true. Okay, the Lewis dot structures, I went through this. Now I'm showing it to you. 1, 2, 3, steric number 3. 1, 2, 3, steric number 4. Lone pair here. Okay, so 3 and 4. We're not finished yet. And so this was trigonal planar. This was tetrahedral. And with this, the bond angle is 120 and 107 degrees. Why is it 107? Why not 109 degrees? Because you have the lone pair effect. Good. But I didn't ask you for the angle. Right? But I asked you for the magnitude of the angle. So because it was so fun, let's do another one. We want to have a linear molecule. We have a central molecule and a central atom and 2 other atoms. Iodine dichloride minus, bromine difluoride plus, and H2S. Okay, so obviously that S is here, that Br is here, that iodine is here, and so you put the chlorines, the fluorines, and the sulfur around it, and then you try to see what kind of a steric number you have, and you give me an answer. This is a tricky question. It's not a trick question, it's a tricky question, okay? So what's H2S? S has how many? 6. And hydrogen has 1, 6, so 8, okay? How many free electron pairs do we have there? You need to practice this. So I'll give you a hint. ICl2 minus has an expanded octet. You know that now, okay? ICl2 has an expanded octet. Quite a few lone pairs. Which of the following is linear? You want to call somebody? Okay. All right. Yeah, that's expected. And so I'm going to give you the solution that you say, why didn't I get that? So Lewis dot structure. Sulfur has 6, isn't that? No, 6, yeah. Hydrogen has 1, so you have 1 from the hydrogen, 1 from here, 2, 4, 6, okay? So that's the structure. So what would the steric number be of that? 4, isn't that right? 4, so that would be linear? No, it would be tetrahedral, not linear. What is this one? Bromine and fluorine plus 2 fluorines is 3 times 7 is 21, is 20 electrons, isn't that right? 20, yeah? So you have 2 free electron pairs. That would be 1, 2, 3, steric number is 4, exactly. Also tetrahedral. Okay, now here the steric number, iodine dichloride minus, so this is 3 times 7 is 21, and 1 minus is 22. Iodine and chlorine is in the same group, 21, so you put this up here, you have 3 free electron pairs, And so in this case, you put them right here, okay? And with this you have a bond angle of a bent bond angle here, and this one is linear. You see that? Because the 3 pairs are here, and of course they can push as much as they want, and they still keep it linear, all right? That's a difficult issue, but it's the examples in your book. Look at your book, there's a very nice page. I see, one second. I won't be here on Wednesday. There will be one of the, don't worry. There's a very good GSI who will be teaching for me. You will have a lot of fun. I have to give a talk in Washington, D.C., and I will be back on Friday. There will be no office hour. I wish you a good weekend. Bye-bye.